Entropy, Part 1, Definition. We will define the number of microstates and entropy, the number of states and temperature, and the second law in equilibrium. Why the second law of thermodynamics should interest you? Because this law affects all aspects of our life. It says that the entropy of the universe tends to increase and never decrease. In this series of 2 clips, we apply this law to a set of balls and boxes and explain entropy and its outcomes, the long-tail distribution, the normal distribution, and information. What is entropy? Entropy is a physical quantity, yet it is different from any other quantity in nature. It is defined only for a system in state of equilibrium, and it tends to increase. Entropy tendency to increase is the source of all the changes in our universe. Entropy tendency to increase is the tendency of the nature, including us humans, to make energy flow in an irreversible way. Irreversible energy flow is responsible for the order created in nature, like life and its outcome, like cities, industry, knowledge, and also for decay and death. There are many misconceptions on the meaning of entropy. Some say that entropy is a measure of disorder, which is not true. Some say that entropy of a file is not entropy, which is also not true. Entropy is a measure of uncertainty. Therefore, to understand it, we have to consider its true probability. To do so, we consider an ensemble of boxes and balls in which all the balls are randomly distributed in the boxes. We assume that each box may have any number of balls. Entropy is defined in a closed system. A closed system is a system in which both the number of boxes and the number of balls are fixed. A ball is an undividable, non-interactive amount of something, i.e. quantum of energy, an atom, an identical object, etc. All the balls are indistinguishable. All the boxes are distinguishable. They are the same, but in different locations. For this ensemble, we will define 2 basic probabilistic measures: the number of microstates and the number of states. From these measures, we will derive 2 basic physical quantities, the entropy and the temperature. The connection between this probabilistic measure and the physical quantity is the second law of thermodynamics. Microstate definition. A microstate is a distinguishable distribution of the balls in the boxes. In a closed system, all microstates have the same number of boxes and the same number of balls. Example: if we have 2 balls and 2 boxes, we have 3 microstates: 2 and 0, 1 and 1, and 0 and 2. If we have 3 balls and 2 boxes, we have 4 microstates: 3 and 0, 2 and 1, 1 and 2, and 0 and 3. The number of microstates is designated by capital W. The entropy S is proportional to the logarithm of the number of the microstates. Why? If the system can equally be found in one of the W microstates, the uncertainty is therefore proportional to W. Why the logarithm? To make the entropy additive. In physics, it's called extensive. If 2 systems have W1 and W2 microstates respectively, then the combined system has W1 multiplied by W2 microstates, and the entropy will be S1 plus S2. State definition. A state is a group of all the boxes that have an identical number of balls. Boxes without balls are not counted. Important to remember, a state is not a box. All the boxes with the same number of balls are one state. A state is also called a mode. For example, in our first case, we have two boxes and two balls. We have two states, 1 and 2. In the second case, we have three balls, and therefore we have three states, 1, 2, and 3. The number of states is designated by n. The number of state n is limited by the total number of the balls, p. The average number of the balls in a state is n average, p over n. Total number of balls divided by the number of states. This quantity is proportional to the temperature. Why? If a ball is maybe a unit of energy, more balls mean more energy and higher temperature. Now let's look in our example of two boxes and two balls. N average is 1. In the second example, N average is also 1. Why? Because we have three balls and three states. The second law of thermodynamics states that the entropy has a propensity to grow. In a closed system, it will go to some distribution of balls in the boxes that has the maximum number of microstates, and therefore has a maximum entropy. When the entropy is maximal, the system is stable. The point where the entropy is maximal, it cannot grow anymore, and therefore the distribution is stable, is called equilibrium. Therefore, the second law can be defined as follows. A closed system tends to reach equilibrium. Since the average number of balls in a state, n, is proportional to the temperature, and the second law of thermodynamics tends to equalize temperature because heat's flow from hot to cold is an irreversible process. Therefore, the temperature of all states in equilibrium are the same, and all states in equilibrium have identical n average. The total number of balls in the ensemble is P equal to the number of states multiplied by n average. Now look at an example of P balls in 10 boxes. The number of states is 10, and the average number of balls is equal to 1 in the state. The number of microstates is, however, from the combinatoric, it's 92,378. Now I ask a practical question. What is the probability to find a box with one ball, two ball, three ball, etc.? Since all the microstates have the same probability, we have to write down all the 92,378 microstates of the system and count the number of all the boxes with one ball, two ball, till 10, and divide this number by the total number of the occupied boxes in the total number of 10 multiplied by 92,378 boxes. This is a horrendous job. However, the second law of thermodynamics gives us a golden rule. Since the states have the same n average, which in our example is 1, then if a state I comprises of I boxes having n eyeballs each, and all the states have identical n average, then ni multiplied by I is equal to the number of states multiplied by n average. Then we can easily calculate the number of boxes with a given number of balls. Does nature obey these statistics? Yes, it does, and we will see it in part 2. The Boltzmann constant is a universal constant of nature. Boltzmann constants connect between the probabilistic boxes and Boltz's measure to the thermodynamics dimensional quantity, namely S, the entropy, in joule per degrees Kelvin is equal to Kb ln W. The average N is equal to kBt, and the total energy is given by N multiplied by N average is equal to N kBt. Why all this is relevant to us? Because this definition enables us to calculate the distribution of the bolts in the boxes for our ensemble. This equilibrium statistical distribution are the statistics found in nature. They are outcome of the second law of thermodynamics and the propensity of the entropy to grow to its maximum, namely to a state of equilibrium. Some recommended reading material, and I want to thank to Chava and Udi Kafri, Ezriel Hasid, and Yossi Bogen for their help. Thank you.